Welcome to another CVB202 practical, available potassium in soils. Potassium is an essential mineral for all life. So essential is potassium to plant life that it is quite common to talk about the NKP ratio, that is the nitrogen, potassium and phosphorus ratio of a fertilizer. In soils, potassium is derived from the weathering of feldspars and micas. Most potassium in soils is strongly bound to these volcanic minerals, and it is not until these volcanic minerals are weathered that the potassium becomes available to the roots of the plants. In this practical, we will measure the potassium which is available to plants in a sample of garden soil which has been used to grow vegetables. We will do this utilizing flame atomic emission spectroscopy. The soil used in this practical was used as received and was weighed by difference into a plastic bottle. In this case, the soil in the container weighed 5.4549 grams, while the residue in the container weighed 4.3197 grams after the sample was tipped into the plastic bottle. To the soil in this bottle, 50 ml of an ammonium acetate acetic acid buffer was added using a Class A volumetric pipette. This was placed onto a shaker unit for 40 minutes to ensure complete extraction. Once the extraction was complete, a filtration apparatus was set up using a fluted filter paper. The solution from the soil extract was filtered using this apparatus into a beaker. The analyst in this case carefully decanted the solution to avoid tipping too many solids onto the filter paper. A series of standards in 50 ml Class A volumetric flasks was made. A volume of 1000 ppm potassium standard was pipetted using an auto pipetter which was calibrated in the previous practical. Volumes of 0, 0.1, 0.2, 0.3, 0.4 and 0.5 mils were pipetted into the 50 ml flasks and diluted up to the mark using the ammonium acetate acetic acid buffer. As with the previous practical, by ensuring we are using the same diluent as in our sample and standards, we are ensuring they are matrix matched as best as we can. Once the sample and the standards were prepared, it was time to run them on the flame atomic emission spectrophotometer. Flame atomic spectrophotometers are simple instruments when compared to flame atomic absorption spectrophotometers. In the case of this spectrometer, all controls are available on the front of the instrument. These include the air-fuel ratio for controlling the temperature of the flame, the blank control for adjusting the blank for the background emission of the flame, the detector sensitivity, and the optical glass filter. If we look at the energy level diagram, also known as a Grottian diagram, for potassium, we find the 4s orbitals are occupied, while the 5s and the 4p and the 5p orbitals are unoccupied. In this case, the p orbitals are split due to the coupling of these orbitals. In atomic absorption spectroscopy, if an electron absorbs a photon with the same energy as the energy difference between the 4s and the 4p orbitals, the electron is excited to the 4p orbital. It is this absorption that is used in absorption spectroscopy. When an electron relaxes back to the ground 4s state from the excited state, it releases a photon of light equal to the difference in energy between the two orbitals. This is the process of atomic emission spectroscopy, but in this case, the excitation of electrons occurs by the absorption of thermal energy, not light energy. In the case of potassium, the main emission lines of potassium arise from the transitions between the split 4p and 5p orbitals back to the ground state orbital, the 4s orbital. This gives rise to emission lines that are red and blue-violet, but in this case, the analytical lines used are the red 766 and 769 nanometer lines. To select these and reject the emission lines of other elements, an optical filter is used. On the spectrophotometer, there are several filters which can be used depending on the analyte being analyzed. These filters select only a narrow selection of the spectrum applicable to the element of interest and remove any potential interfering line. The sample is introduced into the spectrophotometer through a nebulizer which uses the air for the flame to make tiny droplets of the solution. As with other forms of atomic spectroscopy, most of the sample is rejected and finds its way into the waste container at the back of the instrument. This is the glass container at the back that you can see here. The standards in the sample were run on the spectrophotometer starting with the blank sample. This blank sample was set to a reading of 0 using the dial on the front of the instrument. Each standard was run from the least concentrated to the most concentrated. The sample was then run on the spectrophotometer. It was noticed that the reading from this sample was greater than the most concentrated sample. The sample was diluted by mixing 5 mL of the sample with 5 mL of buffer before being rerun on the spectrophotometer. The calibration curve was checked using QUT calib to ensure the QC was below 5%. Again, in this practical, please remember to calculate your concentration of potassium all the way back to the soil sample, and don't forget to propagate your uncertainty.